It was around 6 p.m. on June 24th, 2026, when the ground beneath northern Venezuela suddenly began to shake violently. It split open, not once, but twice under a minute. Two back-to-back earthquakes tore through the same fault system, unzipping 200 kilometers of Earth's crust from the coastal mountains all the way to the capital, Caracas. By the time the shaking stopped, roughly 90 seconds later, more than 5,000 people had lost their lives. Over 16,000 were injured, tens of thousands were missing, and an estimated $37 billion in damage had been left in its wake. Caracas suffered heavy destruction, but the state of La Guaira took the hardest hit, where nearly 80% of the buildings collapsed. This was not a normal earthquake followed by an aftershock. This was something far rarer and far more destructive. A magnitude 7.2 quake, followed immediately by an even larger 7.5 rupture. This was a seismic doublet. So to understand how a catastrophe of this scale could happen, and why two massive earthquakes struck back to back, we have to look beneath the surface at the mechanics of our planet. Earthquakes happen when rock under immense tectonic stress suddenly breaks along a fracture zone called a fault. While these fault networks can be messy and complex, geologists normally categorize them into three primary types, based on the direction that the rock masses move relative to one another. We have the normal fault, the reverse fault, and the strike-slip fault. Geologists also use two terms from the 19th century mining to describe fault anatomy: the footwall, which is the block of rock below the fault slope where the miner would stand, and the hanging wall, which is the block above the slope where the miner would hang their lantern. Something to note is that when a reverse fault has a very shallow slope, less than 45 degrees, it is called a thrust fault. These generate the planet's most powerful megathrust earthquakes and massive tsunamis, such as the magnitude 9.1 megathrust earthquake that struck offshore off the coast of Japan in 2011. In a normal fault, tectonic forces pull the crust apart, causing the hanging wall to slide downward along the slope. In a reverse fault, the exact opposite happens. Intense compression forces the crust together, pushing the hanging wall up and over the footwall. And finally, in a strike-slip fault, blocks of rock slide horizontally past one another, almost like a zipper, with little to no vertical movement. This brings us back to Venezuela. Northern Venezuela sits directly on one of the world's most volatile continental boundaries, the collision zone between the Caribbean plate and the South American plate. This boundary isn't a single clean break, it's a sprawling 1,500 kilometer scar known as the Boconó-San Sebastián-El Pilar fault system. For centuries, the Caribbean plate has been grinding eastward past Venezuela at a rate of roughly 2.2 centimeters per year. So that might sound slow, but over decades that friction locks the rock in place, storing colossal amounts of elastic strain energy along a massive right lateral strike-slip network. On June 24th, two adjacent heavily locked segments of this system unleashed its energy, causing two massive earthquakes 39 seconds apart. So now we know that they were strike-slip faults that caused the two earthquakes that evening. But what caused the second earthquake to trigger? This is known as a seismic doublet. It is when two large earthquakes of similar magnitude happen close in time and location, where the first event transfers energy or stress to a nearby fault, which then triggers the second event. When the first magnitude 7.2 rupture tore through the Boconó segment, it didn't just release centuries of built-up tectonic strain, it displaced it eastward along the fault line. It slammed directly into the adjacent San Sebastián segment, a section of rock that was already locked, loaded, and at its tipping point. 39 seconds later, the second domino fell. The magnitude 7.5 rupture didn't just add to the destruction, it multiplied it. To make matters even worse, the Hypocenter, which is the underground origin of the quake, was extremely shallow. triggering at a depth of only 10 kilometers, or roughly 6 miles. Because the energy had so little distance to travel to reach the surface epicenter, the shockwaves arrived with devastating, unchecked intensity. The Boconó-San Sebastián-El Pilar fault system had been quiet for decades, silently accumulating tension every single year. On June 24, 2026, that tension was released in just 90 seconds. It's a humbling reminder that while we build our cities on what feels like solid ground, we are only ever leasing space on a dynamic, restless planet. One that is constantly in motion beneath our feet. The scariest part? Scientists cannot currently predict earthquakes. They can only detect the rupture once it has already begun, giving us just a couple of seconds of warning before the shockwaves arrive. If you found this breakdown valuable, please consider subscribing. We cover the world's most fascinating phenomena, one video at a time. We'd also love to hear from you. Have you ever experienced an earthquake, or do you live in a seismically active region? Let us know down in the comments. Also, a huge thank you to everyone for the incredible support on our last video about El Niño. The numbers absolutely blew us away. Y como siempre, mantén la curiosidad y nos vemos en un próximo video. ¡Saludos!